Good afternoon, everybody. My name is Shanshan Li. I'm a master's student in Jinan University in China. Today, I would like to present our research about digital twin architecture for production logistics, the critical role of programmable logic controllers. This presentation includes 4 parts: the research background and method, then the process we do the study, and finally the conclusion of this study. In recent years, governments around the globe promote the technological advancement of manufacturing through policies such as Industrial 4.0, Smart Manufacturing, and Made in China 2025. We can find that most of these enabling technologies of advanced manufacturing are inseparable from the acquisition, storage, and utilization of industrial data. So in this context, new modeling approaches that aim at real-time data processing and control, such as real-time simulation, proactive simulation, or digital twin, gained prominence. Among them, digital twin is one of the top 10 strategic technology trends of 2021. Gartner predicts that the digital twin market is to grow from $3.8 billion in 2019 to $35.8 billion by 2025. So what is digital twin? A digital twin is a term that was given to the concept of a virtual digital equivalent of a physical product. In manufacturing, digital twin technology plays a role as a simulator and optimizer. It enables the detailed visualization of the production process and fast, automated response. The main difference between simulation and digital twin is time, which is presented in this table. Digital twin can not only collect real-time data from the physical object automatically, but also create real-time reaction, while simulation cannot do it or do it with delay. With the common target of increasing productivity, competitiveness, and efficiency, industrial applications of digital twin focus on the areas of design, production, prognostics, and health management, with specific focus on maintenance of equivalent and quality assurance of the product. However, we found that few research about digital twin applying to production logistics and materials flow control. This comes quite as a surprise given the need to make quick decisions in this context, which should make digital twin a key technology. We argue that there were mainly 2 reasons that hinder the application of digital twin to production logistics and material flow control, that is, modeling detail and data structure. Digital twin tend to be large-scale system models that use centralized data structures, just like the figure in the left side. A big advantage of large-scale models is that data handling is simplified, but it leads to problems if the physical object used for the twin is moving, because this increases the complexity of data collection, storage, and handling. The use of decentralized models also imposes much higher complexities in terms of data input or output. So here we proposed a new architecture to build digital twins in area of production logistics. See the figure in the right side. For moving products, we think it is more meaningful if information is stored on the object in the form of digital encapsulated information. This then allows for the creation of a hierarchy of twins, where products and resource twins create higher-level system twins based on a decentralized data structure. To prove the feasibility of this new approach to build digital twins, this study uses action design research to build the first prototype of a digital twin of a small lab-scale production environment. It seeks to implement the hierarchical structure presented in the literature and to base this structure on product twins in addition to resource twins. Note that the objective of this study is not the realization of the new train architecture, but the identification of potential challenges for future research. So, what is action design research? Action design research is a research method for generating prescriptive design knowledge through building and evaluating ensemble ID artifacts in an organizational setting. It is similar to a classical PDCA circle and has 4 stages. First, we should formulate the problem. Then, according to the problem formulation, start building, intervention, and evaluation. After that, we would get some reflection and learning about this research problem, which allows us to revise the problem formulation. Repeat this circle for several times, and finally, the formalization of learning can lead us to a deeper understanding of this research. The purpose of using action design research is to gain both practical and theoretical insights from the perspective of design science. So we start from the stage 1 of action design research. Digital twin is a key enabling technology for advances in manufacturing, but its use is restricted to equipment and large products produced in fixed position layouts. Given the current focus on large-scale system models and centralized data and computer structures, in this context, we start our study with the following design problem. Can a new digital twin architecture be developed that uses local product and resource twins to create higher-level system twins? Then we come to the stage 2, building the architecture in practice. Before building a digital twin, a series of questions needs to be answered. Firstly, which object is to be answered? Physiotechnic Industry 4.0 model factory is used in this study since it provides a relatively cheap alternative for testing. And then which aspects of the object are to be shadowed? So individual products and resources is to be shadowed in this study, and the measures to be shadowed are the resource state and the routing state of the products. Then how to process the information we get, and what are the real-time control actions taken in this research. As we mainly focus on the building of the architecture of digital twins, so only simple methods are applied and simple actions are taken. The first 3 questions determine whether we can create the digital shadow or real-time simulation, and the last 2 questions determine whether we can create the proactive simulation or digital twin. According to the answer of the questions above, we design a solution of building a centralized digital twin of production logistics. There are 3 layers in this architecture, including the physical layer, the communication layer, and the virtual spaces. All the sensor data is transmitted to the virtual spaces through PLC here, and using this data, we can build a digital shadow of the physical object. By data processing and analysis, the status of the physical entity is presented in virtual spaces. If any problem appears, the control center can make fast decisions and create real-time reaction to the physical entities to solve the problems. The detailed steps for building a first centralized digital twin can be summarized as follows. And this is the picture of the digital twin prototype. There were several issues which led to reflections and learning outcomes. Firstly, transferring data from the sensor to the computer is a problem. Many scientific studies on data processing start with a data set. This overlooks the problems and biases associated with getting sensor data into the computer in a format that can be accessed by data processing software. Secondly, software and hardware is often incompatible. This also led to the problem of creating real action from a computer result. These problems were even more pronounced when we sought to shift the loci of the train from the centralized cloud to the individual objects. While it is technically easy to digitally store information as a product, adding the required intelligence to create a digital twin is more challenging. Further, the smart object itself also needs to interact with the application layer to create an action. How to store data, process data, and how to realize actions at the smart object level is a major challenge that needs to be solved before decentralized part trains can be created. So from all of the above issues, we get the learning that PLC is an integral part of any digital twin application, which receives insufficient research attention. The capability of a digital twin is largely determined by the PLC capability. In fact, it may be argued that the PLC itself is a first-order digital twin. PLC often provides the only solution to actually build a digital shadow and create real-time reaction. For real-time simulation, data has to be directly transferred from the sensors into data that can be handled by the software used for modeling and analysis. So this study contributes to the existing literature in several ways. In theoretical perspective, this study outlines a new system architecture for digital twin, that is the hierarchical twin, and it also identifies a major barrier to the realization of this new architecture. PLC capabilities are likely to restrict any digital twin application. From the practical perspective, we learned that digital twin technology can be used within semi-autonomous collectives of machines, equipment, operators, and mobile devices. Simple solutions such as Arduino boards and open-source software may provide an alternative to often costly commercial solutions. The limitation of this study is that this study is only focused on the feature-technic industry model factory, while this provides a pre-built lab-scale manufacturing environment, and it is fully automated. So using a self-built factory in which material can accumulate and queues occur provides a better means to test our proposed architecture. Future research is needed to explore the vital link between PLC and digital twin, includes research on wireless networks and PLCs. For example, the communication protocols such as MQTT and technological advances such as 5G. To realize the wireless data input and control of actuators in real time. We should also explore the control architectures that link the different levels in the hierarchical digital twin. This is all of our study. Thank you for your listening.